Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to start into a series on review of rational functions. It'll be a high-level review. In fact, you'll be introduced to new concepts within rational functions. So just as a reminder, we're going to use this specific video to kind of cover topics that you are kind of a high-level view of topics that you should be familiar with. So the very first one is the definition of a rational function. You should be familiar with this from your intermediate algebra course. A rational function is just a function that's a ratio of polynomials. That's really what that means. So there's a lot of different kinds of rational functions, or looks to rational functions, I should say. One such rational function would be something like 3x squared plus 1 over maybe negative 6x minus 2. That's a ratio of polynomials. Also, maybe I'll call that r sub 1 of x and this r sub 2 of x. You could have x plus 1 over x. Whoops, I don't know what I just did there, but x plus 1 over x. That's a ratio of polynomials, so that's a rational function. Finally, what you commonly see in a textbook is a ratio of prefactored functions like x minus 1 times x plus 3 all over maybe 3x plus 1 times 2x minus 7 or something like that. So all of these are just ratios of polynomials, so therefore they are rational functions. The last one in that list is a prefactored rational function. And really the ultimate goal with rational functions is to get them factored. That's kind of the big ideal that we would like to reach with rational functions. And whenever you're dealing with rational functions, probably the biggest topic, I mean really the huge topic that you have to be highly aware of, are the rational functions asymptotes. So an asymptote, there are two types, actually there are technically three types of asymptotes. You have vertical asymptotes, you have horizontal asymptotes, and then you have something called slant or oblique asymptotes. And slant or oblique asymptotes we're not going to worry about in this specific video, but I'll talk about them a little bit later. But you should know that vertical asymptotes generally occur when you have division by zero. Now that's not always true, actually, but for now, we'll just say it's generally is true. The true definition of a vertical asymptote, at least the true non-calculus definition, is if your function that you're looking at, your rational function, or it doesn't actually have to be a rational function, but for our purposes, we'll say for our rational function. So if your rational function tends to plus or minus infinity. So the y values go to infinity or negative infinity as x gets really close to some constant a. Then f is said to have a vertical asymptote at x equals a. To really put this into perspective, let's just take a look at a random rational function. I'm just going to randomly draw one here. Let's pretend that we have a rational function that looks like this. And then I'll put in a little dashed red line there. And I will have maybe on the other side something like this. Okay. So that, if I say that happens, that red line happens at x equals, let's say 3, then because the function that I've drawn is going toward infinity, right? The y values are climbing without bound as x gets really close to 3. Those y values just keep climbing up. That means that x equals 3 is a vertical asymptote by definition. That is, the function values In that case, we're going to positive infinity as x was approaching 3. Therefore, that must be a vertical asymptote, just by definition. Same thing on the other side. By the way, the y values, or the function values, were diving down toward negative infinity. So again, it's just telling us kind of a repeated idea that that is a vertical asymptote. Now, it's not necessary for a function to go to infinity on both sides of an asymptote. For example, I could draw out a vertical asymptote. Again, I'll use x equals 3 here. And maybe on the left-hand side, your function might look like this. As it gets really close to the vertical asymptote, it might rise up to infinity. So therefore, just that alone, the fact that the left part of this graph is rising to infinity as x is getting really close to 3, that tells us this is a vertical asymptote, that x equals 3 is a vertical asymptote. Now, strangely, it could be the case that on the other side, your function might look like this. I put a little open hole there to say that as the function gets really close to x equals 3, so this might be x equals 3.5, and this might be x equals 3.1, the values, the y values, are reaching some height. So at 3.5, they're at this height. A little bit later, here and here and here. Eventually, they're getting really close to some y value, which we don't know. We could say it's y equals 1. It doesn't really matter. But the fact is that open hole means that the function will never actually exist at 3. It gets really close to x equals 3, but the function doesn't actually exist at 3. But x equals 3 is still considered a vertical asymptote because one side of it, on one side of x equals 3, the function is rising to infinity. Therefore, it is still considered a vertical asymptote. The function I've drawn here is a rarity, but it does occur. It's this is not actually the graph of it, but an example of a function that looks like this is y equals 2 raised to the 1 over x power. It looks sort of like this, not exactly. Now, it's worth stating that because when you graph rational functions, you sometimes get holes in the graph. It's worth stating that a hole in your graph is not a vertical asymptote. So just be very aware. The full definition of a vertical asymptote is that the function, what that green curve is there, its y values have to run to positive or negative infinity as x gets close to a finite number a. If this is some finite number a, x equals a, notice that the function does not rush off to infinity on both sides or on either side of x equals a. So therefore, x equals a is just a hole in the graph. It's not a vertical asymptote. Now let's spend a little bit of time just recalling what a horizontal asymptote is. So I'm going to erase this highlighter, and now we're going to focus quite a bit on the horizontal asymptotes. So if our function values, again, these are y values. That's what a function value is. So if our y values are approaching, that's what the arrow means, approaching. So if our y values are approaching some value of k, maybe 3 or 10 or something like that, as x goes to positive or negative infinity. So it could just be approaching the value of, let's say, 3 as x goes to positive infinity, but not as x goes to negative infinity. Then f is said to have a horizontal asymptote at y equals k. Again, let me just demonstrate a few different styles of horizontal asymptotes. So one could be like this. So I will say that we have a vertical asymptote, and I hope you don't mind. I'm just going to draw a non-dashed vertical line just because drawing dashed lines tends to take forever. So I'm going to say this occurs at x equals negative 5. And we have, let's pretend, our function diving down and reaching down to a height of 0, it looks like, as x goes to negative infinity. And maybe on the other side, it's trying to reach a height of 0 as x goes to positive infinity. Again, let me say that. Over on this side, as x runs off to negative infinity, The y values, which are the function values, maybe I should just say f of x, approach 0. The y values are getting closer and closer to a height of 0. Along the same lines, as x goes to positive infinity, in that direction, right? The function values also seem to be approaching 0. So this is said to have a horizontal asymptote at 0. So I usually say it this way: HA is at y equals 0. Horizontal asymptote at a height of 0. Now there are, I should say, a bunch of other examples. I'm going to give one here. Suppose that maybe we do have a vertical asymptote on the y-axis. Let's just pretend. And then you have a horizontal asymptote here at a height of 1, and maybe a horizontal asymptote on this side at a height of -1. That actually does happen more frequently than you may be aware of. And let's pretend that our function looks like this otherwise. Now I'm specifically drawing out some characteristics that might surprise you. The first thing that I need to say is that functions can never intersect their vertical asymptotes. In fact, that's so important that I want to write that down below. I'm just going to write it right here. So again, a function will never touch its vertical asymptote. So these, you can see both branches, that's what we call these, both branches. This is the right branch, that's the left branch. Both branches of this function tend to the vertical asymptote, but don't touch the vertical asymptote. And it's a vertical asymptote, by the way, again, just to remind you, because at least on one side of this vertical asymptote, the function values are heading to either positive or negative infinity. Once you have one side doing that, it's already a vertical asymptote. Now let's just concentrate on the right branch here. Notice as x goes to infinity, the function values tend to some height, right? So it looks like they're tending to a height of 1. And so therefore we would say that this function has a horizontal asymptote at y equals 1. And the behavior is that as x goes to infinity, the function values approach 1. Now let's look at the left branch. The left branch is very interesting. The first thing I should note, and it's somewhat obvious, is that as x tends to negative infinity, so as we start looking far to the left, the function values here are tending to a -1 in height. Right? They want to approach this height of -1. So this function happens to have two horizontal asymptotes, one to the right and one to the left. I'll just go ahead and box that up and call that a horizontal asymptote as well. So it is possible for a function to have two horizontal asymptotes. It won't have more than two, but it can have at most two horizontal asymptotes. The reason why it can't have more than two is because the way the horizontal asymptotes are defined. If you look at the definition, you need x to approach infinity and something to happen, and then x to approach negative infinity and something to happen. So there's only two options there, one to positive infinity and one to negative infinity. So just be aware of that. And then the other thing I want to draw your attention to is that while I did tell you a function cannot intersect its vertical asymptote, it turns out that a function can intersect its horizontal asymptote. In fact, it could do it an infinite number of times. So I'm just letting you know that a function can and likely will actually cross its horizontal asymptote. I shouldn't say likely, but often does. Maybe I should say it that way. And there we have it written down. So these are the big concepts with rational functions, is that they generally do have horizontal and vertical asymptotes. And we are going to focus in the future videos on finding these and developing methods to really make it easy to find these horizontal and vertical asymptotes. In general, vertical asymptotes are incredibly easy to find, and once you get used to it, so are horizontals. Now, I do want to mention one last thing here. Not all functions have a horizontal or vertical asymptote. Rational functions generally have vertical asymptotes, but actually not necessary. It's not necessary, I'm sorry, because, for example, the function x plus 1 over x squared plus 1, that function right there, does not have a vertical asymptote. It does have a horizontal, but it doesn't have a vertical asymptote. So there's just something to be said about rational functions and the fact that, yes, they all actually have horizontal asymptotes, but they rarely have, actually, no, they don't all have horizontal asymptotes. Some have slant and obliques. So basically all bets are off. They sometimes have horizontal asymptotes, they sometimes don't. They sometimes have vertical asymptotes, they sometimes don't.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.